Okay, hello everyone. Thank you so much for joining today. Sorry for the few minutes of delay. We were setting everything up. So we have with us here today Ricardo Enriquez. He holds a Ph.D. in physics from Universidad Complutense de Madrid, and he has a long trajectory as a researcher, mainly in disruptive technologies that help accelerate the energy transition, mainly with institutions such as CIEMAT or the International Energy Agency. At the moment, he belongs to the Advanced Mathematics Department in Repsol, and he's the head of the Quantum Advisory Team. That's a multidisciplinary team that was created in Repsol in order to guide the company's quantum journey. And in addition to that, he collaborates regularly as a teacher, both in graduate and postgraduate programs in several universities in Spain. So his talk today is going to be titled Quantum Computing Applications for the Energy Sector. And Ricardo, it's so nice to have you here. Thank you so much for accepting the talk, and all yours.
Well, thank you very much. Good afternoon, and thank you for the kind introduction and the kind invitation to this important master. I think that we all here, we are thinking that this is a very promising technology, and it's very important to promote them and to see how in different fields we could in the future use this. I saw just a housekeeping first, small. I saw that this is recording the session. Rafael.
Sorry, I was on mute. Yeah.
Okay, I think it is not a problem if it is just for the UPM purposes only. I need it's mandatory for us to say this in Repsol.
Okay, maybe let me.
Yeah, it's not a problem to record, but it is only for this master purposes.
Okay, let me quickly stop the recording there. I'm going to pause it.
Thank you and good afternoon. Okay, yes, I'm Ricardo Enriquez Miranda. I'm the head of Quantum in Repsol. And what I want to show you today is some opportunities and some initiatives for the energy sector from quantum computing, and mainly focus on what Repsol is doing right now. That is probably the most interesting part that I can offer to you. So we will have, I think they told me I have more or less a 1 hour talk, and this is more or less the syllabus I will follow. So first we will look for some kind of the energy context and what are the energy challenges we are facing today, and what are the quantum computing opportunities we can find in this sector. Then I will spend some minutes talking about how Repsol is involved in the quantum journey, and I will present also an Spanish initiative with the aim also to become an international initiative somehow. That is the project QCO. It's a Spanish project, I will tell you. And finally, I will try to have time enough to show you some use cases and see how are we facing these challenges for our own products. So let's move to the energy context. And yeah, it's a commonplace today to say that we have climate change. And we have global warming, and is one of the biggest challenges. A lot of people talk about the space race, but climate change is probably the biggest technological challenge mankind is facing. If we look to what do we need to do is mainly to reduce CO2 emissions, and moving to big institutions such as the International Energy Agency, that every year publish 2 very important reports related to energy, very important for big companies and for countries and municipalities and authorities, so it's a big reference. What is the World Energy Outlook? Is, let's say, how is perform in the world related to energy. And the other one is the technology energy perspective. This is what should we do to do this? And you can see in the figure that we have a current trend. If we do not do anything, we will move beyond, well beyond a 4 or 5 degrees Celsius global warming. If we want to reduce this global warming to an acceptable, sustainable scenario, we need to do a lot of things. And you can see here that we have more or less the blue, light blue, and different scales of blue that are somehow energy efficiency, just taken for 1/3, let's say, of the common emissions, is building, power, light, and so on. And you can also see that there are some other third that is including low carbon generation sources that for sure are renewables, but also you can find here nuclear energy in some flavors. This is to 2050. And the last pillar of the emissions reduction are the carbon capture and utilization and storage, for sure. And we're related to different places. I mean that it is not only reducing emissions, but probably we will need in the future to get out CO2 gases from the atmosphere. Well, when we move to quantum computing, or just computing, I mean, in this scenario, what can we do? We can do in all parts, we can do optimization, we can do simulation. And presently, it is called machine learning. This is taking statistics and data mining and getting something from the data. We can do all over the value chain and all the sectors. In efficiency, mainly in probably efficiency is the best part to do optimization and to enable with the control and communications to perform advanced control systems for energy systems. Simulation is probably more devoted to design new and to optimize and to strengthen the power of energy sources. And machine learning are also a way of behavioral change, or the way we have to use a lot of big data to manage this. So what is true for computing in general is true for quantum computing in particular. I mean, quantum computing is a new flavor of computing, and this. Well, this is let's say, some kind of a crisis. It's a big opportunity for technologies that are disruptive, such as quantum computing. Well, this is the one side of the energy sector. And the other side is if we are looking to the future, we need to look for what are the energy sources, what can we do? And this is some very famous global energy resources related that what are renewable. I mean, you can see here that you can provide in an annual basis all this kind of energy. This small ball here is the total world energy consumption per year. And I must say that this is not very scientifically correct, because this is power. It should be terawatts hour. I mean, so sorry about that. This is an imprecision from the source I got this, but you can see that from the older renewables, solar is the biggest one. So we need to exploit this source. It's difficult because this has a low density, and we need big surfaces. But we need to understand better the interaction of radiation and matter. And to do that, probably quantum computing can help us. That's hopefully we will see today. And there are other sources, of course, but there are sources that they are not so renewable. I mean, that they have an end, and we have some reserves. And this is more or less the picture here. So related to this, what can we do? This is more or less our game board where we need to play and what can we do at this moment. So, well, all the technologies, quantum computing is, as you probably, as your teachers told you, there are different ways of quantum computing, and all of them can, in principle, be a part of this mix of technologies. What I want to say is that quantum computing is not a definite technology. For sure, there are some kind of mainstreams, and you can see that there are adiabatic quantum computing that, as you know, is to mainly solve optimization problems of some kind, that you establish some kind of Hamiltonian of a system, of a known system, and you perturb in an adiabatic way that system to look for the ground energy configuration and as a solution of an optimization problem that you map into. Another very promising and probably the most famous is the gate-based quantum computing paradigm. That is quite similar to the good old computers. You have gates and you have some qubits that you are performing transformation on the qubits as gates, but the difference is that the qubit is not a bit and have some spectacular properties that we can use in our benefit. For sure, there are other paradigms, and one of the others is the one-way quantum computing, also called measurement-based quantum computing, that you produce, in this paradigm, you produce some kind of reservoir state, quantum state, and you perform sequentially measurements, and the measurements are acting on the quantum state in a way that the measurements are the answer to a typical problem. And finally, the most common applications and the most ready, commercial ready applications are the quantum-inspired one, just being from software, so tensor networks or hardware, also digital annealers, that are the systems that somehow emulate, are inspired by this quantum behavior to obtain some computational advantage. Well, these are paradigms that when it's happening here and quantum computing, how can we expect what? And you can see here some roadmap, and we see that it has been a long trajectory of theoretical work, and now we are living an interesting time, because probably in the next 2 or 3 years we expect to have some what is called the quantum advantage. Well, what is expected really? We will not have for sure the what is called the fault-tolerant quantum computing. So we will need to adapt our algorithms to the NISQ era. This is a near-term quantum computing. This is the noisy intermediate scale quantum. So we will have probably in the upcoming years 1 to 10,000 qubits with no correction errors. And okay, this is a common place, and we will try to find some kind of advantage in this scenario. Well, let's move to the applications. And what the first thing is to know what others are doing. Well, the first place to look at is the academy, and the academy is looking for the old problems, are well-known old problems in the energy sector, where you have difficulties with the classical computing, and you know that they are really hard problems. And I put in this slide some of them, just for you, and some papers and recent reviews you can look at to see and to have a taste what is going on there. And I must say at this moment that just being aware of what is happening it's hard. I mean, there are a lot of case studies, and you need to spend some time. This is highly beyond this talk to enumerate, just to enumerate all the cases in the different sectors, just from generation, for distribution, for storage, or for end use of the energy. And just some examples, you can see here a common old problems, such as this is a heat exchanger synthesis. I mean, it's the design of the heat exchangers for industrial processes, where you try to maximize the energy recovery from the different processes that are subject to constraints for production and temperatures and all the operational constraints related to the production of the manufacturing of a product. This is commonly used many in the oil and gas sector. These are refineries, for instance. Heat exchanger synthesis is a very big problem. There are some methodologies, but they can be improved very much. Also, where do you put the facilities? The facility allocation problem is also a well-known and hard problem, and we are far from solving it in a precise and good way. We do what we can, and how old and when do you leave the what we call the irons and the refinery and so on? When you move from one place to other, when you close a facility and put and open another one, it's not common, it's not easy also. And finally, you can see here, the unit combined problem is the problem of where the energy units are switched on and off, taking into account that they have some kind of thermal inertia to provide some profile for the energy demand. And okay, this is also a difficult problem for computing, and we spend a lot of computing time. I encourage you to read again. You will find in these reviews and applications to nuclear, renewables, energy grid stabilization, and so on. So I will not deep into this part. And also, it's good to know what others are doing, since the feeling I get is that the first to come is the first to win. I mean, nobody, and that's a matter of fact, some years ago, when we were saying the people that we need to move to quantum, and most of the directors and managers said, Ricardo, why quantum? Will it be for sure possible? Is this a hype somehow? And now I can tell you that the mainstream idea is, what is the differential, the breakthrough, and what should we do in a differential way? And you can see that several, the most of the big players of the energy sectors, mainly they are focusing on one partnership. Let's say ExxonMobil is with IBM. A lot of people is moving with IBM. BP was with Cambridge Computing, maybe. Total, you can see here, and you can also Electricity de France, EDF, move to a partnership with Pascal, and they are focusing on one or two or three called killer applications for to enhance their own business. So you have here, for instance, Total is dealing with CO2 captured by metal organic frameworks are very difficult catalyzed reactions for chemistry, and they are moving to that application just to be the first one to do that and to get the quantum advantage. Okay, in this context, I would like to spend some minutes and to explain how is Repsol moving to this place. And okay, some figures, some of my slides are in Spanish. I didn't find the right one in English, but I think there are some numbers, and you can figure out what is happening. And the idea is Repsol probably is famous for the gas stations, but in fact, the reality is highly different. And Repsol is what is called a multi-energetic company that exploits very, very different sources, such renewables. In fact, we have more than 1.5 gigawatts of renewables installed in all over the world. And we have also a spirit of innovation that it is not very well known. And this is some kind of a photograph of our technology lab where I come from, and we are less people, but close to 300 people of scientists devoted to very different fields. So the tradition of innovation of Repsol is very high. So it's changing again and again. And what is very, very less known for sure is that Repsol was the first company to announce the 2050 emissions, net zero emissions commitment. Was the first company all over the world to say, and others follow, just to say that in 2050 we will have net zero emissions in our operation. This is not an easy task. So we saw that there is a quantum revolution. I like to say that it is a continuous revolution, and the quantum revolution happened probably 100 years ago, when we moved first to discover quantum somehow, and to have something like a photovoltaic effect. In fact, was the Nobel Prize Award for Einstein. And you cannot understand the energy landscape today without photovoltaics. So if we want to be there in the future, we need to understand this new revolution, the second quantum revolution. And okay, the good thing, the idea is to let's put a group, an interdisciplinary group that we call here the Quantum Advisory Team. We are leading this to figure out how to advise the company to early adopt this technology. And thinking about that, this is the computing for the future. Nobody can claim that this is the computing for today. So we need to link this to the problems of the Repsol's future, that are those related to energy transition. For sure, we need to do this by identifying some partners, but we do not want to say, like others did a couple of years ago, that we are moving right with the hand of IBM, Google, so on. We need to explore by our own, and that's an important question. Every company, every startup need to understand what, and to realize what is their objectives and their personalized quantum journey. There's no two quantum journeys that are not equal. And also we would like to put this in an open innovation methodology, taking into account startups and ecosystem and so on. Well, this is something about me. Is the leadership. It's not stressed at all. So yeah, this was some kind of a joke, but no, I mean, what I try to figure out with this picture is that when you try to introduce new technology in an ecosystem that is highly technified, the other technologies react. You cannot expect they open their arms and say, okay, for sure, come here and move everything. But there's an engineering topic that if it is working, don't touch. So we need to deal somehow with this kind. So we just look for hybrid solutions. I mean, if it is quantum, I think is better. I'm a quantum optimist, but we are also working with other players such as the Barcelona Supercomputing Center. And what we need to figure out is how to enhance the performance of our products and our processes. So for us, we'll be agnostic from the quantum point of view. And in fact, if you ask my opinion, somehow, I think in the near future, the hybrid solutions in some the classical computers are very good to perform some tasks. And the quantum computers will be some kind of a small add-on, at least in the next 5 years. For so that, okay, this is an opinion. Well, for sure, we want to be a big player of this industrial revolution, this new industrial quantum revolution, and we will look for alliances and startups and try to accelerate this process. So this is more or less our view, and different companies have different views, but for sure that I can tell you that most of the companies nowadays have a view. And closely related to these activities, and I told you we need a framework. I want to tell you to speak another couple of minutes about one project. It's a QCOS project. This is a Spanish project, and that's the way we look for enhancing quantum computing in Repsol. I mean, it's to look for other partners and to share the risk and to ask for some funding to minimize the risk. And this happened by the end of 2021, when we have the chance to move with other big players in Spain to move to a project. It's a 3 years duration. It's 2021 to 2024, and we put some different industrial sectors. You have GMV is from aerospace, Samatec is from logistics, BBVA is a big bank from Spain, from the finance sector. Repsol, for sure, and we have the leadership of what we call the quantum computing for a sustainable energy sector. DAS Photonics make some things for signal processing, communications, and they are related also to the defense sector. Kilimanjaro is a startup, experts on quantum hardware, also some software, but mainly hardware. Multiverse Computing is a startup that is devoted to quantum software, and you can see there more or less the big players from the research centers such as Barcelona Supercomputing Center, CSIC, Tecnalia, the Photonic Institute from Catalonia, and the Donostia International Physics Center, and also university. Well, what do we expect? Moving more and more into the details. So when we need to perform quantum computing, we need to figure out what kind of applications will be the first to kick on and the first quick wins. So the quantum computing for optimization. And optimization, we think, will be the first hitting time. So we started first with the quantum cases for optimization. The next one probably is not in the next 2 years, but the chemistry applications, since the quantum languages is the natural languages for chemistry and for the microscopic world. And also, finally, quantum computing for machine learning we'll put at the end. And this is not, the argument is as follows. So this is machine learning. They need to deal first with a big amount of data, and that this is not easy task for the capabilities of the actual quantum hardware. And the other argument is that Repsol has a strong artificial intelligence strategy. And what do we want to do is to check where can we expect quantum advantage just by in a standalone basis. If you mix quantum computing and artificial intelligence somehow, probably you will not get a very clear idea of if you get an advantage, so which part came from. So we just want to check for quantum by as a standalone, and okay, then when we realize where are the advantage, we can mix with other technologies. You can see here, I encourage you to look for the QCT project website for actualizations and so on. So as any project, we have, sorry, this is again in Spanish, but this is very easy to know that we have 3 work packages. The first one is devoted to the use cases construction. The second one is the quantum algorithms development and R&D, and the third one when we will execute some of them. So we have some partial executions. I can show you today some small partial results about it, but we are running on this project, and you will need to wait for more news as to realize how is performing this. We are working on it at this moment. Just to notice that we are the leaders of these 2 lines. This is molecular simulation and the optimization lines of research. So what we do, sorry, this is in Spain. What we did is to put a lot of key users for our use cases that you can see in the vertical lines, and we figure out what are the different technologies we can use. You can see here the BQE or the QAWA stochastic optimization, but also we want to figure out how to low TRL technologies such as Gaussian boson sampling or quantum walks can have something to say about optimization, and for different use cases that I will tell you about in a couple of minutes. Yes, let me, okay. Yeah, the idea is that through these cases and through these lines, we can figure out how different partners in the QCT project can collaborate and can share the risk. And the other thing I want to point out from this slide, and we have a quantum computing expertise, but the biggest expertise is the expertise we shared between the owners of the use cases, that they know their problem very well, and the quantum computing part. And the most profitable job profile we need today is someone that is understanding both. We need professionals that they are understanding their own problems from the classical point of view and from the industrial point of view, and also have knowledge of quantum computing techniques. Yeah, that's what I wanted to say at this moment. So now I move to what are the activities in quantum computing with more or less detail about this. And these are related to the use cases we move into the QCT project. So this is not, in principle, is not a public, it's not a public information. So this is only only for your eyes somehow. Community choice aggregation, the optimal control somehow, and the quantum chemistry applications. Well, community choice aggregation is the first one. Is related to the participation in electricity markets, in the majorist electricity markets, what is called some places the pool, the energy pool, that probably in the recent days or months, the price of the energy has been very high, and you saw in the news many times the price of the electricity. And this was the idea is that with our technologies, we can produce some kind of a virtual power plant. I mean, a power plant to participate in electricity market are most important engineering installation or wonder, engineering wonder, is the grid. And we need to preserve the grid. We do not want to burn the grid. And if you want to penetrate some renewables, you need to make a balance between the supply and demand. And that balance needs to be fixed at the order of seconds. And how do you deal with this? You put, when you consume your energy, the energy started trading probably months or even some year ago. And when you move closer and closer and closer to the consumption instant, different markets fulfill the differences. And the last markets that are dealing with the last hour or even the last quarter of an hour are called the ancillary services. In Spain, it's called mercados de ajuste, and they are an opportunity to participate there. The news about this is that mainly the most of this participation came from big plants. I mean, some hydro combined cycles that they can react somehow. But, and this is a very big but, that you can aggregate a lot of PV installations, and not only PV installations, but also batteries, vehicle fleets, and to produce some kind of power plant that is virtual, is made of very small parts. And this is a big effort of coordination and control. Also from the legal point of view, this was the first installations of this kind. It was at the west coast of the US. This is probably in California. This is the first thing. This is called the common aggregation communities somehow, and they put some legal framework to do this, and then we moved to Switzerland. And in Spain, this was, if I don't remember, well, it was 2020. This is highly recent. The idea of this problem is that you have some houses, with some devices, let's say dishwasher, let's say washing the laundry, to make the laundry, and you have some or domestic heater for hot water, domestic hot water, or even the air conditioning, that is there suitable to be controlled somehow, that when the electricity market needs to match supply and demand and ask for these ancillary services, you can react as a swarm in a coordinated and orchestrated way. Well, we need to do that to have advanced control system installed in different homes. So you need to be some kind of big player in the energy sector. And then when you have an advanced control system, you need to figure out how to do this. And you need to do this to provide an offer with 24 hours ahead from the electricity market. So you need to forecast somehow what will be your energy consumption. And then once you have provided one forecast of the energy consumption, you need to know how can you deviate from this forecasted energy to a potential participation of your consumption. So you can participate in this. Well, this is a big optimization problem because, as I told you, you can participate as an aggregated system, but you need to fulfill some requirements. And one of the requirements is the minimum power allowed. I mean, I'm not very confident, but for sure it will be at least 10 megawatts. If you think about one home is about 5 kilowatts, but 5 kilowatts are not what we call the controllable devices. So the manageable devices are probably at most 1 kilowatt per home. So we are dealing with, for one of these units, we need 10,000 homes. And for 10,000 homes, we have the minimum amount. But if you want to make some business related to this, probably you need to have at least 10 times this. So you here are these figures that if you need 100,000 people, and to solve a problem that they have at least 1,000 variables and constraints per home, because as I told you, you need to figure out the 24-hour ahead, and it is called a model predictive control in an open loop way, and you need to do this every 15 minutes. It's a big problem. And what we did, when we are phasing out is the first, we ask for each home that tell us what we call the flexibility. You can also see here, so flexibility in the literature is called flexibility services. So we can calculate for each hour, each home, what can they do, and then we can move to put an optimization problem to touch all the different flexibilities and to perform an offer. Well, this is a very hard problem from classical computing side, where we move this problem to quantum computing framework. And what we did is to move to perform some benchmark. We did this with the Barcelona supercomputing, Barcelona supercomputing center, and we make a synthetic problem from this problem, just to benchmark, and we move to different parts of the problem, and to check both, to check the algorithm we want to employ, and to check also the hardware where we are running, and to see how the hardware is running out. Well, the results from this part, the full results will be also out of the scope of this talk, and probably most of the parts are confidential, but I can show you. So to calculate the offer, what we do is we look for an annealer. Oh, sorry. Okay, yeah. So we translate the classical problem to the Ising Hamiltonian as usual, and we need to take into account that there are a lot of difficulties here. First of all, is that you need to figure out that the Hamiltonian you are producing has an energy gap. And this is not an easy question. I mean, it's, as far as I see, it's one undecidable problem from the mathematical point of view. And okay, you also need, when it is very easy from the mathematical point of view to put what is called the mixed integral nonlinear problem. But when you have a lot of restrictions like this, you need a lot of qubits for to deal with the slack variables, to put all the constraints into the Hamiltonian. And you need also to figure out the Lagrange multipliers you are using. You need to make some fine tuning, and sometimes you do it by hand. But as I told you, in a small problem, let's say in finance, they have problems dealing with 2, 3, 4, 7 Lagrange multipliers. So the quantum analysts that I've been talking to, they do it by hand, and they can do it because there are a few parameters. But when you have, let's say, 1,000, 2,000 parameters, it is not easy to make the fine-tuning, and you need to also develop new techniques, some machine learning one. And we also observed that when you move to these devices, D-wave, but not only D-wave, that are quantum, real quantum annealer. It's a native adiabatic evolution. It can be better, but it's a true one. But also the simulation ones, the quantum-inspired ones, such as quantum-inspired optimization from Microsoft. When you try to use all the variables that are available in the devices, there's some kind of effect of saturation somehow of your model, and some part of the constraints are not fulfilled. So it is not so straightforward to say that I can put this from the theoretical point of view. For sure, this is good, but I can say one phrase here from Albert Einstein. They say, in theory and practice are the same. In practice, they are not. So this is the case. When you move to the real device, you figure out, you face some problems. Okay, and I can show you here a small result of this. You can see here the runtime from different algorithms, and this is the number of, okay, this is a kind of the size of the problem. And when we can see here, that this is the classical one classical solver we use here. Here is the D-wave hybrid machine, and you can see that you can get more and more size of the problem with the same runtime. Okay, this is the quantum inspired solution. It is performing worse, but it's good anyway. But the really amazing is I think this is the brilliance. It is not brilliance. I cannot remember the name. This brilliance is from Xanadu, and Sycamore is from Google's, and Pegasus. I think this is the Pegasus chip, and you can see here that the computing time is fairly good, related to the classical and the other solutions. They imply classical computing, but, and this is a very big but, the amount of qubits, even more if you take into account that you need to use a lot of qubits for slack variables in problems like this, but then you cannot get sizes of the problem that are very big. But in principle, hardware can solve that. Well, let's move to at least I'm watching the clock, and I realize that I need to come to an end, but I want at least to give you a taste of other two problems related to the Repsol's activities. The other one is the optimal control. The optimal control is very ubiquitous, and then we have three different use cases in CUCO related to Repsol. that deal with this problem. So our approach is to solve the optimal control problem, try to figure out a quantum advantage, and then from a general framework, try to see how difficult it is to apply it for different scenarios and see. And the other scenarios we have selected, that are also coming from the energy transition scenarios I told you. One is the green hydrogen production by electrolysis that probably you heard about hydrogen economy and the importance of hydrogen in the future. The other one is to deal with utilities networks. How do you demand hydrogen, but not only hydrogen, also heat and electricity and so on for your industrial processes? A refinery is a very, very big, complex industrial site, and there are a lot of links, and the network is highly complicated. And in fact, there are a lot of people devoted to artificial intelligence are working hard to optimize the operation of a refinery as a whole. So we can expect that quantum computing can do something there. And it's also related to the first one, because you need to produce green hydrogen when you need it, otherwise you need to store it, and it's not easy to store the hydrogen and so on. And the other one is the planning for the biofuels. Biofuels is not a will, it's a must. Because the European energy, European Union is mandatory to have a part of bio component for fuels. For fuels, just every kind of fuel, aviation, sea transport, heavy duty, or even cars. You need to a part needs to be bio, and also not only bio, but they need to fulfill some characteristics in that bio. That means that when you have a demand for a country like Spain, that we have 5 sites, we need to figure out how to get the waste and which kind of waste and how to process that waste to our new refineries. That we are calling the biorefineries, are the same place, but the technology is different for the future. It's a big planning problem from the optimization part, but we are convinced that we can all these problems put in the form of this is called the optimal control problem. And we consider this is an open problem for the quantum community. And I don't know if you want to do, you need to do a master thesis or a project of somehow. But if someone wants to do something in this case from Repsol, I kindly invite him to do. And the problem in a mathematical form is just that you have the functional that you want to minimize or to maximize to get an extreme, and it's subject to a differential equation that is a constraint of this problem. And I cannot tell you at this moment what the solution is, because I don't know, and we are exploring this at this moment. But we have, I can tell you at least the approaches we are following to figure out how can we do. And we have 2 strategies. The first strategy is discretize the problem, because this is a continuous problem. This is an integral, and you have continuous, it's functional. And then, okay, discretize for your time and eventually spatial steps, put on a grid or a mesh. And discretize also, from the temporal point of view, the dynamics in the form of the differential equation to, let's say, adopting a finite difference scheme. Once you have done this, you can map this to a combinatorial optimization problem somehow, and you can put into an annealer. But you can also do it with some heuristics, because it's a discrete problem. You need to figure out somehow that you can use a mathematical technique called evolutionary computing. Now, this based is genetic algorithms, particle swarm optimization, ant colony, and this kind of algorithms or heuristics that it's called. And also these heuristics, probably we can use, and we can figure out how to use quantum walks to enhance those kind of solutions. For sure, once you have put this way, you can use other gate-based algorithms such as QAA, BQE, imaginary time evolution, and so on. So this is one part of the solution, and the other one is to be even more quantum and say, to figure out how can you map this problem to the Schrodinger's equation. Schrodinger's equation is a partial differential equation, but this has a lot to do with how quantum devices are doing. And not only, but also you can, if you want to not to be so much quantum, you can use a quantum algorithm to invert matrices to the HHL algorithm, and to figure out how to get a quantum advantage here. The Schrödinger equation, you can try to solve it by Hamiltonian simulation, and there are some papers. It's a recent developments point out there, but, and this is a very big but, the hardware needs to be enhanced quite a lot, and the success is not assured. So as I tell you, this is a problem, that this is an open problem, but the reward is very high, because this problem is highly ubiquitous in the industry, not only in energy, but energy in particular. This problem can also be mapped, the optimal control problem, to the finance sector. Well, I think I'm running out of time, but I want to spend at least a couple of minutes to talk about chemistry. And chemistry, it has a course of the exponential difficulty of solving the Schrodinger's equation. The chemistry problem, you can map this problem to the calculation of the ground state of an electronic configuration of a molecule. And this problem, if you want to solve it in a classical way, it is impossible. You cannot do it, and you need to do approximations. And the more crude approximation you do, the less precise you are. So as you can see here, to understand this, probably you need to be a physicist, or at least a strong quantum chemistry. I don't want to get inside just to save time for questions. The idea is the most common approach is, it is not a matter of the size of the problem, but it's the matter of the physical approach and the mathematical approach of our theories, such as DFT is one of the most wide applied theory for quantum chemistry, and DFT stands for density functional theory, and this is some kind of simplification that you do with the hypothesis that the electrons are not highly correlated among them. And you can see here that for some situations you cannot even decide if something is touching or not one surface. I mean, the theory does not allow, so we figure out. You can also see here in a different case that in a strongly correlated system with highly quantum effects, the theoretical values are far from the experimentally true values, so we can expect there. A couple of words more about quantum computing for chemistry, in that the biggest advantages expected, the supremacy expected, they are for fault tolerant. I mean, the phase estimation is far from us. We will need to make these calculations 5 million qubits to figure out the situation. So we, as I told you, we moved to the NISQ era, and probably we need to use variational quantum eigensolver, the VQE. Probably you heard in your class, and not only VQE, but there are also improvements about imaginary time evolution. And when you use this, well, you can do a small part of the molecule. So you need to do, what you need to do is to mix, to embed some kind of results coming from density functional theory, and try to move the quantum part to the quantum computer, just to catch the quantum effects. So we are exploring this at this moment. We are based in you can read something about the IBM's people are also doing great things. And the main application will be the catalyst for hydrogen production. In our case, you can see here some kind of artist representation of the water molecule. And we are dealing with some mixture and to figure out how to use different quantum technologies, such as quantum annealers, gate-based computers and tensor networks, and we are working on it. So hopefully in the upcoming future, I can tell you how to solve this Hamiltonian in the second quantization form, and how to deal with the different devices to say present some results. Finally, last but not least, the quantum advantage, it is expected from the energy side, probably it is not a calculation. It is not a better calculation or a faster calculation, but it is that to do just the same as classical computing, we can spend 3 or 4 times less energy. Probably that's all we need to get a quantum advantage. Well, there's some estimates from Google's Sycamore. We have some kind of 25 kilowatts, something like that. When we know that high performance and supercomputer stands for megawatts. So we are dealing, and we are also measuring this in the QCOS project. We will do it by the Mare Nostrum facilities from the supercomputing center of Barcelona. And we will also measure the energy of some quantum devices to perform some similar. And we will check, and we will provide results hopefully next year. So this is more or less all I wanted to say today. For some parts, I need to go fast, but I'm yours if you have any questions about activities, quantum computing in general, or so on. So last, just to say goodbye, thank you. And don't forget, I started with the sun, the solar energy, that stare at the sun. So quantum computing is a tool, but we need to figure out how to solve the problem, taking into account the big picture. Thank you very much.
Thank you so much, Ricardo, for the great talk. Are there any questions from the audience? Anything you want to discuss with Ricardo? Feel free to drop them in the chat. In the meantime, there's already one that came in the first minutes of the talk. I think it's a bit off topic, but maybe we can discuss it in the meantime. So basically, you showed a graph where we indicated the different amount of energy that we can retrieve from each one of the different sources, like solar, carbon, and so on. And Oscar Novo, I think it is, yeah, was wondering if there are any numbers or any considerations about fusion energy. It's a bit off topic, but maybe it's interesting to discuss that. That's the one.
Any, sorry,
Yeah, so we have uranium there, and he was asking if there's any reference, any estimates on how much we could get from fusion energy, from nuclear fusion.
A nuclear fusion, yeah. No, I sorry, I cannot provide it. This is coming from an article from Richard Perez. So if you Google it, you can find it. And when Richard did this, there was no fusion. Was now is coming. Yeah, no, but I cannot provide because nuclear fusion. I cannot provide the number, but probably I can say a couple of words. It is not about resource because you can calculate there. Let's say if I have some tritium and deuterium and so on, and this is my potential, but that's not true because you need to see how much of this potential the technology can provide in some kind of performance of the reactors and so on. So I think it is not an easy number to do, but it's a great question. Yeah.
Okay, thank you. Yeah, it was a bit new, but in any case. Okay, I don't know if there are any other questions. There's one from Jose Miguel Jimenez. So basically, how do you handle the real-time component of that one optimization solution that is based on quantum annealing? If you need to apply the solutions in closed control loops, changing the position of valves. So basically, how do we handle the real-time complexity when we are using these algorithms?
Yes, okay, that's a nice question. I would like to, I don't know if, I would like to see the people. I don't know how to because sorry.
You can also jump in and open the microphone. That's completely fine also.
Yes.
Oh. Yeah, I'm trying, sorry, but I'm trying to see the faces of the people.
There you are.
Can you see me, Ricardo?
Yeah. No,
okay.
I cannot see you. I just see my this okay, probably. Okay, now I can see you. Okay. Yes. Well, the question is, how do we deal with real time? And this is also a very big question. So don't forget that what we are doing here is to provide some kind of proof of concept. So we are far from a real-time application on a real device for an optimal control. That's completely true. But we can figure out, let me please switch my my light because I'm seeing that I'm very dark at this moment. So give me a second. Okay, well, this is a low consumption bulb, so we need to wait. Okay, yeah, this is a proof of concept. We are far from being there. So we have two different approaches. The first approach is to move to the cloud and to ask for the control signals at the high level coming from the cloud in a regular basis. So then the technical approach is to deal with computing and communications latency. And then you put a constraint that your computation needs to be performed, let's say, in 3 minutes at most, because you need every 15 minutes your control signal. So that's one approach, and you can have a buffer of different horizons of control, and if you do not get the communication, you are just following the same plan. until you can, that's a common approach. And there's another approach that I have not speak here today, but we are also exploring, not in Goko's project. It's mainly activity I told you today, but there are also activities that this is quantum algorithm co-design, and this is related to some annealers, and there are some startups and some researchers that are doing things with not very big annealers, small annealers that can enhance some parts of the problem, and you can use it locally. That's a device that you can have on premise on your installation there, and you can perform calculations from typical control schemes, and with let's say a laptop and a small annealer, in principle you can fine-tune the control. That's another. Are people working on annealers that you can put on premise? But that's more futuristic, I think. The main idea is to get this, and probably from optimal control. It depends on what do you really understand for real time. Below
20 seconds, 10 seconds, 5 seconds. Is to communicate with a programmable logic controller, to change the position.
No, for sure not. I'm thinking about more, when I say optimal control, is about model predictive control, that we are not dealing with PIDs or no, it's not such a level. It's a level, let's say, more, it's more similar to planning, more than, or scheduling, more than, more than control of the real device. No. The approach is, I think, the industrial, but that happens in refineries, in conventional refineries. We have controls that operate, that they give, that operates on a highest level, that you have the units are controlled by PIDs. But your real control move is a DMC, dynamic matrix controller, or something like that. It's more sophisticated and gives the set points for the control.
Yes, we used to manage some, for example, refrigeration plants, and we give the solutions to some equations, multilinear equations, using, for example, evolutive or genetic algorithms, working on neural networks. You have a surrogate model, and you can have a physical model with components of predictive models and an optimization model running in the top, and searching for the optimal solutions to minimize or to maximize an output, and with some constraints in the inputs. And we manage that, and we need to communicate with the PLCs, with the programmable logic controllers, to change the set points or the timers of the hysteresis of some loops. It's another approach, but it's quantum computing.
I think classical. For sure, quantum computing will not be at the field level for the real time. That's true, because you need just communication, and the most I tell you, the most sophisticated thing we show is this kind of small annealers that they are developing just to do something, but it's highly sophisticated. It is unclear that we can get an advantage there. So it's a good place for research, but it is unclear. For sure, I agree on that. So I don't know how many people do we have. Well, I don't know, Rafa, or I just want to offer. Okay, my email is there, and I don't know if there are some people that need to make the the end of the master thesis.
Yeah, I can provide you with that information, so we can actually share, for example.
I don't know if I fulfill the requirements as a teacher to do. I mean, but I can offer, and for these problems, this for sure, small instances of mainly the optimal control problem I stated today. We have a lot of subtasks to do. It's a big problem. So it will be helpful, and if someone is motivated to do, I think we can do something there.
Definitely. For example, last Monday, we had 4 students from the previous edition. They presented their master thesis, and 2 of them were focused on logistic applications and other types of applications that are relevant for the industry. So let me drop you an email. We can discuss that in more detail, and maybe if there's any topic that is relevant, maybe some of the students is interested in developing that.
It's just an offer. And from our side, we have a lot of work to do, I mean, and probably we can explore less things that we would like, as always. So this is a public project in the KUKOS, and it will be also very, I think, to see from the government and the administration. I think they will see very, very good initiative to do, but okay, it's up for sure, up to you and up to the students somehow for sure. But okay, we can discuss this.
Yeah. Okay, that's perfect. And thank you so much, Ricardo, for the offer and for the talk. I think it was amazing. I hope everyone in the talks liked it. So we will now move on to the next speaker. Thank you so much, Ricardo. Have a nice day. We will drop you an email with the last details. And
thank you very much, and feel free to send me any feedback about this, because as I told you in the first time, I didn't realize what was the technical level of this. So I hope it was more or less good. Yeah. Okay. Thank you very much.
Thank you, Ricardo.
Okay.
Thank you.